Okay, so we're doing section 3.3 now. The derivative of trig functions. Derivatives of trig functions. And there's really a couple ways of going about this. The first way is we're going to use this technique, but we want to consider two limits. The limit as theta goes to 0 of sine theta over theta, and somehow we need to prove that that is equal to 1. And the other limit that we want to prove before we go into the derivative is that the limit as theta goes to 0 of cosine theta minus 1 over theta is equal to 0. And that's in a different video. Okay, and we prove these two statements in that video. Okay, so we're going to focus just on the derivative geometrically, and then we'll look at the algebraic argument. Okay, so let's take a look at the geometric or graphical derivative first, so we kind of know what to expect out of the derivative. And so I will draw a picture of the sine function. Kind of like the sine function. Oh, let's do one more period. Oh, half a period. We'll get the other half over here. Good. So this is the sine of theta over theta. Over theta. God. Versus theta. Squeaky chair, sorry about that. If you've been watching my videos, though, you know that's what's happening there. Someday I need to get my chair oiled up. Okay, so what I want to do here is I want to graph the derivative of the sine. And so when I'm graphing the derivative, I always go after the zeros first. And so remember that this is where the derivative is 0, where it's got a horizontal tangent line, horizontal tangent line, horizontal tangent line. So the zeros are going to be here and here and here and here, and it looks like this is about the value 1, which looks like it's going to be the maximum. So that's going to be about there. This is, if that's a 1, then that's about a -1, and this is just an approximation, right? So don't get wild on me here. That's about as negative as we get. Positive, then it goes to 0, positive 1. Okay, you're getting the idea. -1 down here. And you're seeing the curve here. What's the curve looking like? Do you recognize that curve? If you've had calculus before, don't ruin the surprise. Okay. This is the cosine of theta. So the derivative of the sine of theta is equal to cosine theta. Good. All right. Now we're going to prove this. By the way, this is just a kind of a geometric, hand-wavy kind of thing, because you've got to believe, right, that the value here was equal to 1 and the value there was -1, +1, -1, right? Okay, good. Similarly, since we have the cosine right here, let's go ahead and take the derivative. Let's see what so this is taking the derivative of cosine and see what we get. So again, it's typical to, let me pull the camera over a little bit so I don't have to move my paper. Okay, so again, we look for the zeros. So here's a 0, here's a 0, here's a 0, if you believe my work. 0, 0, 0. This is about a -1? Oh, +1. What am I talking about? It's a +1. There's a -1. And there's a +1. There's a -1. What does this look like? Are you seeing it yet? What curve does that look like? Is it the sine wave? No, it's not the sine wave. It's minus the sine wave. If we take negative sign, these would all flip down, and so we would get this. And so we see that the derivative of cosine of theta is minus the sine of theta. Okay, so this is the end result of what we're going to get, but I don't want to leave it there, right? I think proving things by pictures has its place, but we ought to be able to take a look, especially using these two limits, to see if we can prove that these derivatives are what they need to be using our definition. Good. So let's take a look at the definition. What does the definition say? This one's... Okay, I just had to grab this trig sum formula. So we're going to need a sum and difference formula, and so I'm going to use this formula when we take our derivative. So let's see. Let's see where that comes in. Let's go ahead and write down what the derivative is from our definition. We have the limit as h goes to 0 of the sine x plus h minus the sine of x divided by h. Right, and now what is the sine of x plus h? If you read this off, you see that I can rewrite that as the limit as h goes to 0 of the sine of x cosine of h plus the sine of x plus h times the cosine of x. Oops, wait a minute, something's wrong. Oop. That was just the sine of h, right? Sorry about that, cosine of x. And it's dark there too. Okay, minus the sine of x divided by h. Very good. Now, do you see anything useful out of this expression? It would be really nice to be able to factor this sign out. So how about if I take this guy and attach it to this guy? I'll just regroup them together, and notice that I could factor out the sign from that. So I'm going to go ahead and write that over here. That's the sine of x if I factor it out, times cosine of h minus 1 divided by h. Good. And then this other term over here is the sine of h times the cosine, sine of h over h times the cosine of x. And I have a plus sign. Good. Now, is it appropriate for me to write the limit like this? Does this limit exist? Yes, we know that that limit exists, and the limit is 1. This doesn't have an h, so that's fine. Sine of x does not have an h, so that's okay in terms of the limit. Then for this one, do you remember what the limit is? This limit is 0. Good. So therefore we now have that the derivative is cosine of x. Very good. All right. And so in a similar way, you can prove that the derivative of the cosine is minus the sine, but I think I'm going to leave that. So what we've just shown is that the derivative of the sine of x is cosine of x. Okay, and then we just will accept the fact that derivative of cosine of x is minus the sine of x, so we can get the other formulas. So from this, how would I get the derivative formula for example, the secant? What is the derivative of the secant of x? Well, that's going to be the derivative. Do you remember which one? 1 over the cosine of x. Right? And so if we use a product rule, actually we're using the reciprocal rule, right? what would that be? Derivative of the top is 0, so it doesn't matter what's on the bottom, minus the top times the derivative of the bottom divided by the bottom function squared. Okay, so the derivative of the secant is sine over cosine squared. But you might notice that that can be written as sine of x over cosine of x times 1 over cosine of x. 1 over cosine of x is the secant. Sine over cosine is the tangent. Good. So the derivative of secant is secant tangent. All right. So similarly, you can show the following. Let's just go ahead and write down all the rules now in one place. Derivative of sine, I'm going to be building a table. Derivative of sine is cosine. Derivative of cosine is minus the sine. Derivative of tangent is secant squared. I'll let you prove that. And now we look for the other three trig functions. Blah, blah, blah. Secant is secant tangent. Cosecant is going to be minus cosecant cotangent. And cotangent is going to be minus cosecant squared. Okay, now as you're looking at these, the main thing to remember here is the derivative of the co-functions. The derivative of the co-functions. Derivative of co-functions are multiplied by minus 1. Okay. Notice that if the derivative of sine, or let's see, the derivative of tangent is secant squared, derivative of cotangent is minus cosecant squared, right? Derivative of secant is secant tangent, derivative of cosecant is minus cosecant cotangent. And so there is some things happening here in this table that make it a little bit easier to remember. Derivative of tangent is secant squared, so derivative of cotangent is cosecant squared, but then you have to put a negative sign. Okay, so derivative of cotangent is minus cosecant squared. Good. So this is now the end of 3.3. We're just going to be using these formulas now in our toolbox of derivatives. Very good. Okay, I'll come back with some examples before we go anywhere else.